This is video 5 for chapter 20 on cell EMF. This is also section 20.4 in your book. So I just want to remind you that, to do the best job you can and to test well on this, it would help for you to read these sections too along in your book. So what is EMF? Well, we already know that electrons go from the anode to the cathode spontaneously, but what makes them go? And the reason is that electrons flow from anode to cathode because the cathode has a lower electrical potential than the anode. I guess the best analogy I can come up with for you guys to understand this is think of the anode as being at the top of a hill and the cathode being down at the bottom. Now, it's natural for electrons to roll down the hill, but unnatural for them to roll up. So the reason that electrons will go from the anode to cathode is because the cathode has what we call a lower potential energy, and we measure that electrically, so a lower electrical potential energy than the anode. Now, it's measured in volts. And so a volt is the same thing as the energy or difference, potential energy difference required to make 1 joule of energy charge to 1 coulomb. So 1 volt equals 1 joule over a coulomb. And again, when you read this section, that might make a little bit more sense to you, but this volt is a derived unit, and that's what we want you to understand. Now, we call that force that's required to push electrons through the circuit, we call that the electromotive force, or EMF. We can measure the potential difference between the cathode and anode by measuring what we call the cell potential. And that has been given a value of E cell. So E stands for the electrical potential, and cell refers to whatever voltaic cell I've put together. Sometimes we refer to it as the cell voltage. So if I say cell potential, cell voltage, or E cell, I'm asking you to find the same thing in all 3 cases. For a reaction to be spontaneous, E cell has to have a positive value. So keep that in mind. This chapter we're learning that for a cell to be working, it has to have a positive voltage. Okay, so just keep that in mind. Spontaneous reactions have a positive voltage. So think of it like a battery. If a battery is going to work and work something like your cell phone or your remote control for your TV or whatever you're putting batteries in, that cell potential has to be good. It has to be positive. When the battery goes dead, it means that it's dropped down to a negative value. All the electrons have rolled down the hill. Okay. Now, when we want to talk about what is a standard cell potential, okay, so standard cell potential, you guys have seen this before, where we use this little degree symbol. And when we are measuring a standard cell potential, it's just implying that we're at standard state conditions, which for solutions implies 1 molar solutions. If we're talking about gases, we're talking about 1 atmosphere of pressure at 25 degrees Celsius. And we've already looked at this particular voltaic cell, the one that's utilizing zinc and copper. And if you remember the video that I showed you, it has a voltage, a standard cell potential of 1.10 volts, and that's just measured by using a voltmeter. Okay, those of you that are maybe taking physics have seen some of that equipment around, or if you've ever tested a battery and use a voltmeter, or if you do any like kind of simple electrical work at home, you might have seen one of these. Now, where are we going to get these standard reduction potentials? Well, I think there's a small list actually in your chapter, but Appendix E in your textbook is going to have all of them. So Appendix E is something you're going to want to get familiar with, and it's actually something that when you take your exam on chapter 20, I will give you a photocopy of. It's also, these values are also in your IB Chem data booklet. So if you look at page 12, and it's table 14, they have standard electrode potentials for some substances. Now that you know where to find them, what do they mean? Well, all this electrochemical data is tabulated and stored in these tables, and basically all of them are measured to some standard. So the values you're seeing is because they were measured to some standard. And the standard we use was a hydrogen electrode. You can see that reaction below. Now what they do to calculate an actual voltage is they use this formula here, the one in blue, and we're saying any cell potential can be calculated by taking the reduction potential at the cathode and subtract from it the reduction potential at the anode. So let's just, if you have your textbook, look at the Appendix E, and you'll notice some of the values for reduction potentials are positive, others are negative. And the reason is because all of those reactions you see in Appendix E are compared to this standard reaction here. This was assigned a value of 0, and everything was measured according to comparing that reaction with the hydrogen electrode. We call that the standard hydrogen electrode, or SHE. Okay? Now, everything you see in the table in Appendix E, hopefully you're looking at that, or at very least you're looking at your chem data booklet where it's table 14 on page 12. You'll notice that everything is written as a reduction. So for here, like looking at this equation with zinc, you'll see that zinc plus 2 electrons makes zinc solid. When electrons are gained, that is reduction. And you'll see that it has a value of negative 0.76 volts. So because that reduction value is negative, the reduction of zinc as compared to the standard hydrogen electrode is not spontaneous at all. But the oxidation of zinc would be. So this is telling you that zinc is more likely to be able to be oxidized by hydrogen than it is to be reduced. Now when you use the values of these things in Appendix E, you get to use them as is. So never ever change the number from what it says in the table. Because it is an intensive property like density is, it doesn't matter how much of the substance is present. If you have tons of zinc, it's still going to be a negative 0.76 volts when you're looking at its reduction potential. You never ever multiply these voltages, and you'll never ever change the signs on these voltages. You will always use them exactly as they are written in the table. So the best thing to do is to just try a practice problem. So you will definitely want to have Appendix E in your book available so that you can see where I'm getting these numbers. Otherwise, it's not going to make a whole lot of sense to you. And if I check these in the data booklet, I don't think everything you need is listed because the data booklet's a much smaller list compared to your textbook. So what it's saying to do in this problem is to calculate the standard EMF for a cell that employs or uses the following overall cell reaction. Okay, so what this is asking us to find is E cell standard. And so that's your job. Now, knowing what you need to find, it's good to have the formula. So the formula is that we need the reduction potential for the cathode. And from that, we are going to subtract the reduction potential from the anode. And we're going to get these reduction potentials by looking them up in Appendix E. Now, the best thing to do is to split this into half reactions. So let's write each half reaction. So looking at what you have up there, you have aluminum solid, and this has already been balanced for you, so you can keep the 2. And we know that that's forming 2 aluminum ion. Now to get that to balance, we need to add 6 electrons to the right-hand side to negate that charge. Now you're going to look for a reaction that matches this in your Appendix E. Now what you're probably going to see is not 2Al makes 2Al plus 3 plus 6 electrons. What you're going to see in the book is Al makes Al plus 3 electrons. But remember, these cell potentials are independent of amount. So you use the value as is. So look up in your textbook what that value is, and you should see a number of negative 0.166 volts. Now we want to look at the other half reaction. I'll do that one in red. So I have 3 I2 solid, and that makes 6 I minus aqueous. Now you have a charge of -6 on the right hand side, so to this side I have to add, to the left side I have to add 6 electrons. Now you're going to find in Appendix E a reaction that looks like this. But keep in mind that you are probably going to see it as 2 electrons plus I2 makes 3 I minus. Okay? Now use these values as is. And I should probably have mentioned, the reaction in blue was backwards in your book, but that's okay. You just use the values as is. So let's look up this value. Smartboard is being dumb again. So the reduction potential according to Appendix E in the book is a positive 0.536 volts. Now, obviously I'm going to use the 2 numbers that I looked up and I'm going to subtract them. The question is, which one do I write first? Well, let's compare the 2 values. This reduction potential is positive, the one in red, whereas the one in blue is negative. Things that are positive have the greater possibility of being reduced. Remember, every reaction in Appendix E is written as a reduction. So the more positive value is the one that will occur at the cathode. So what I'm looking at here, you can tell that from the reactions too. This was oxidized because it was losing electrons, and this one was reduced because it was gaining. Oxidation always happens at the anode. Reduction always happens at the cathode. So to find the E cell for this particular reaction, I'm going to take the cathode minus the anode value. So a positive 0.536 volts minus a negative 1.66 volts. Now be very careful. I know this is simplistic math. I mean, we're just subtracting, but you would be surprised to hear how many kids will forget that when you subtract a negative, you're really adding. So we get a cell potential of 2.20 volts on this particular problem. Now, there was a lot in that problem that I said that you may or may not have caught, so hopefully this will summarize it for you. Okay, reactions with a positive value for E are spontaneous reduction reactions. So they will happen as they are written. If the value for E is negative, they will happen spontaneously in the reverse way. So they are actually oxidized instead of reduced. The larger your difference between the 2 values, the larger your E cell, and the more positive value of E, the greater the driving force for reduction. So remember, when I went back to this problem, and I was trying to decide which one of these happens at the cathode and which one happens at the anode, the cathode is always the more positive value for E. Lastly, you have to have a voltaic cell that's positive to operate. So I'm going to have you guys try this practice problem on your own without me explaining it. And I want you're going to need Appendix E to do this. And I'm going to give you some hints. Okay, so the first hint I just gave you, use Appendix E, not your data booklet. Secondly, remember, use the values that you look up as is. Do not switch signs, do not multiply them by any values. And remember, when you look up these reactions, the more positive of the 2 E values is the one that happens at the cathode. Now you're going to want to look for reactions that involve cobalt plus 2 to just cobalt, and also silver chloride to silver. That'll give you some hints as to what I want you to find. We'll start with going over this problem in class. Good luck.